As I said, the quantity K has a meaning of curvature. Then, based on the sign of the energy, based on the sign of this constant, the universe has three behaviors. The universe could be closed, open, or flat. Remember, energy is proportional to minus K. So if you have a negative energy, the universe is closed. That means more gravitational energy than kinetic energy. Closed or bounded. That means K is bigger than 0. Energy is less than 0. An open universe has K less than 0. That means that the energy is positive. As we saw, an empty universe has negative K. That makes sense. An empty universe has no matter, therefore no negative gravitational energy. It only has the positive kinetic energy of the expansion, therefore it is open. And the third possibility is a flat universe when K is equal to 0. Now, based on that, we can define the critical density, which is a density that closes the universe. Let's consider again the Friedman equation and set K equals 0 to define the critical density. Now solve for this critical density. Now, to find the numerical value of this critical density, we need to know the Hubble constant. So using the measurement of the Hubble constant, about 70 kilometers per second per megaparsec, translates into a value of the critical density at present of about 947 times 10 to the minus 30 grams per cubic centimeter. Now consider that the mass of hydrogen is about 1.6 times 10 to the minus 24 grams. If you convert this gram per cubic centimeter into cubic meter, that gives you 4 times 4.47 times 10 to the minus 24 grams per cubic meter. So this critical density is about 6 hydrogen atoms per cubic meter, or about 1 hydrogen atom in a cube of side about 2 feet. It's a very small density. And yet, Planck and WMAP measured the density of visible matter in the universe to be about, let's call it rho b, measured by WMAP and Planck, to be about 4 times 10 to the minus 31 grams per cubic centimeter. So lower than the critical density. So if you consider the baryonic mass alone, the universe has less mass than critical density, even though this critical density is very, very small. So the conclusion is baryonic matter alone does not close the universe. The density of baryonic matter in the universe is only 4% of this critical density.